让我们有请诺贝尔物理学奖得主、斯坦福大学教授 Carl Wieman. Please welcome Professor at Stanford University and Nobel Laureate in Physics, Carl Wieman.
Okay, thank you. So, I have a Nobel Prize in Physics, but I'm not going to talk about anything related to that. What I am going to talk about is the other work I've been doing for the last 30 years or so, which is studying the teaching and learning of science, particularly focusing on the nature of expertise and expert problem solving and how we can help students best learn that. And over the past few decades, there's actually been major advances in research in 3 different areas that have given profound new insights on how better to think about the teaching and learning of complex thinking, particularly thinking of things like science and engineering problem solving. And this comes from a little bit from brain research recently, more from the cognitive psychology work that studies at the basic level how the brain thinks and learns, and then work particularly coupled to that, where we put these ideas into classroom, basically experiments and testing done by people like myself, professors in the science disciplines, studying how the students, primarily at higher education, are learning these things. And so we've learned a lot, but this is rather new. Most of this work in the classroom is confined to North America, and so it's not widely known yet, but I'm going to give you a quick summary here. The most basic fundamental result is really, it gives a whole new model for thinking about how learning happens of these complex thinking skills. Now, the old model of learning, which still permeates our education system, particularly at the post-secondary level, is that these student brains come into our classrooms and they vary in different ways, and then we immerse them in knowledge, and it sinks in to different amounts depending on the starting condition of that brain. And when you're using, with that model, basically the primary focus has then been just to first think a lot about what should be in that knowledge soup, what choice of topics to cover, in what order, and so on. And then secondly, how to select the best brains that are going to absorb that knowledge most effectively. So that's the old model, and like I say, it's certainly worldwide, but it's wrong. And what research is giving us is a very different picture of this kind of learning. That in fact, these brains come into the classroom not all that different and highly changeable. And the education process is really transforming and changing those brains in quite a substantial way. And it's doing it by basically changing the neurons, completely changing how the neurons are connected together as a result of intense practice and intense thinking. And it's really in this rewired brain that these improved capabilities, particularly things like problem-solving capabilities in science, really lie. And so you can actually see this now with modern brain imaging. This is a picture here of the brains of 2 people in functional MRI machines interpreting a medical X-ray. And on the right is a medical student who's just learning about how to do this. On the left is an expert radiologist. And you can see how their brains are activated and being used in completely different ways in interpreting this because of their differences in expertise. And another thing that we've learned from the research is that the actual teaching methods matter much more than the particular topics being covered. This is kind of in complete contrast to this model of thinking about learning. And it's because the teaching practices are really the things that determine how much the brain is really exercised, how intense the thinking is going to be doing that results in this changing of how neurons are connected up. So that's kind of the overall principles. I want to show you a couple of examples of the kind of classroom research that supports this, where we're putting in place, like I say, cognitive psychology ideas, and we're seeing, does this actually work in the classroom like we're claiming? So this is work that was done in taking a big first-year university introductory physics class to carefully measured to be virtually identical sections of this course. And it was taught, these two sections were taught in two different ways. One, the control was taught by a person who was very experienced at teaching this material, but used the traditional lecture approach that's almost always, everybody almost uses for teaching such things. And he had good student ratings of his teaching. The experimental course was taught by someone, a fairly new PhD in physics, but had been trained in this research-based teaching. And these two instructors then agreed to cover just the same material and the same amount of class time, and then they had a surprise test they were giving right after they'd covered that unit to see a comparison of how well much the students had learned. So here's the results of that test. And in red, you can see that this is the score on the test versus the number of students here. And on the red is the standard lecture class. Now, on this particular exam, random guessing would give a student about 3. So the amount of learning is really how far above 3 they actually scored. And I think it's pretty obvious from this is that the learning from the traditional good lecture is really tiny. This is quite consistent with other data we've collected. But it's also important to recognize that the research-based teaching here is effective for all students. The entire distribution has moved up. So this isn't something that just is better for the weaker students or the stronger students. It's really better for all the students with a human brain. It's just how the brain learns. Here's a different example, the same kind of teaching comparison, but this is done over an entire semester. And here we have the instructors teaching the 4 core computer science courses at University of California, San Diego. And these instructors switched from the standard lecture format to using these research-based teaching methods, and they looked at the drop and failure rates here. And you can see across the board, there's a dramatic improvement. And so now, using the same teachers, but simply adopting better teaching methods, they have about 1/3 the failure rate that they previously had in these essential courses. So turns out I could give you a lot more examples. I did a review, and there's almost 1,000 published studies across sciences and engineering doing these comparisons of the traditional research-based teaching, the traditional lecture-based teaching with the research-based teaching at different levels and so on. And they consistently show differences in learning and completion for the research-based. And they also show an important fact, which is it's the characteristics of the teacher that really dominate the outcome are strictly what the methods they're using. All these other things about personality and enthusiasm don't really matter very much, certainly at the higher education level. And this is because really it's the teaching methods determine what's going on in the students' brains, how they're thinking about the subject, and that's ultimately what matters. So hopefully, you've seen all these things, you should be wearing, well, okay, what's the secret here? And what makes this research-based teaching so much better? And at the basic level, it just is, instead of students during class sitting there listening to someone tell them information, they're actually having to solve problems. They're working on practicing making the decisions that an expert does in solving problems, and they're working through that together, and they're getting feedback from the instructor during that process. And it turns out practicing making decisions is a lot better way to learn to make decisions than have somebody else tell you what they did. And as I said before, it's really, this is what's required. You have to think about how the brain is getting exercised. That's what develops it. Now, it's actually not, that makes it sound really simple. To do it well, it's not nearly that simple. We wouldn't have had to spend so much time doing research to find out. And so, in fact, at the center here is the key idea of the practicing making decisions that the learner has to do. They have to have good feedback. That means it's got to be, they find out what they're doing wrong or right, but also find out what they're doing wrong and how to improve it and do it in a timely way. That's really critical. But then there's a whole bunch of things that have to go in the design of these practice tasks that they're carrying out, that we've established by research are important. So there's first the disciplinary expertise. They got to be making decisions that an expert in solving problems in the discipline would be making. Those kind of tasks and problems they're giving have to match up with their prior knowledge and level of experience. Motivation, they have to address motivation. That's critically important to get students to be motivated, to put in the intense mental effort that's inherently required to do the sort of brain-changing learning that we are after. And then there's some detailed constraints about how the brain thinks and processes information that you just need to know about and make in these activities. And then when you're actually implementing these in a learning environment, there's certain aspects of the design of tasks and the deliverables of students and ways to enhance the capabilities of social learning to make this work better. So these are all things that research has shown us that, yes, they really do make a difference. You have to know about them and do them right to get the best outcomes. And so, but I think for really the first time ever, these allow us to define teaching expertise in a way that couldn't be done before. In other words, we can now say, look, if a teacher does these sets of things, you can consistently see there will be better student outcomes than if they don't. And there's really not many other things that matter. And so that's really, in some sense, a breakthrough of thinking about teaching, where it's all been so fluffy, you have fads coming and going as to what teachers should be doing. Okay, I'm going to jump a little bit into some aspects of the teaching expertise, the disciplinary expertise side of this, connecting with recent research my group has been doing, really looking in detail at the nature of expert problem solving. What do experts, like faculty or highly successful engineers and companies, do in solving problems in their disciplines? And we've gone through and found that we can identify a particular set of decisions that are made by experts in each of these disciplines. And quite surprisingly, it's essentially the same set of about 30 decisions that are made in expert problem solving. Now, how they make those decisions, that depends very much on the discipline, but it turns out it's independent of the discipline that they have to be making such decisions. So we've been studying that in detail here, and we know a lot about it. We've also established that experts in all of these fields, very early in the problem-solving process, have established what we call a predictive framework. This is just a a mental model which captures the essential features of the context and how those related together so they can make predictions about what would happen. They use this predictive framework then to go through and guide all of their decisions as they're working through the problem. So we found this framework is really useful for actually measuring how well students are learning to solve problems like experts. It means we can basically pose a decision, one of these, a simple scenario, and then compare the expert and student responses. And it's, like I say, it's tremendously revealing. And we find that, students graduating from arguably the best university in the US, if not the world, at Stanford, they come out with lots of knowledge about their subject, but often very little capability of expert problem solving. And so they know knowledge, and this has been most spectacular in the Stanford medical students. They're sort of the elite of the elite. They can pass any test on anything superbly, but when given an actual medical decision to make, they just don't know when and how to use that knowledge to solve problems effectively. And but knowing this, it also shows how to guide instruction. They never learned it because they never had to do it, so we now are working with medical school and actually changing the class, and so it's built around sort of these research-based teaching methods of having students go through and practice making decisions and repeatedly and getting feedback on them. Okay, so there's a lot here about technology. I'm going to spend the last couple minutes talking about the role of technology in enhancing education. And, a lot of, unfortunately, been done with technology is just kind of what it can be done, the lecture has moved from this to this to this, and, we already know and have good data showing that's not very effective, and so pretty certain that neither is watching it on a screen. But so one really has to look for, if you want to have technology effective in education, how can it really enhance, contribute, support these basic principles of learning that we see are established? And one way is just enhanced communication that between student and student instructor that basically helps give better guidance and structure. And there's a number of examples of that. But I'm going to talk about a different direction that I've been involved with, which has really completely new capabilities and nothing else does. And that's these interactive simulations, where you can go to the computer and play around with things and see new things happening. And so they can seek information and to ask questions and answer them. And if these are well designed, and that's a key aspect of this, they can be very engaging and effective for a very wide range of students. And so the project I've been involved with is, and arguably the largest and most successful of these, is something called the PhET project, and it has now used over 100 million times a year in many languages around the world. We make these available for free for different sciences, but they're also being incorporated in a lot of other people's educational products, because that's kind of what we are trying to just benefit everybody's learning through this process. And these are just a couple of examples. In the interest of time, I won't go through details, but you can see how they can explore how atoms fit together, electricity and circuits, the properties of gas, and so on, that we cover in basic physics and chemistry. And the way these really match with the principles of learning is they're highly interactive, that motivates people to explore, but at the same time, they're actively thinking. They're, from the design, it causes them to ask questions, they try and make decisions about what would happen, and then they can go and test those by playing with and seeing, and that feedback and guidance then increases their learning, particularly of these expert mental models that we've seen are so important part of problem solving. So I'm just going to end with a couple movies just showing how these work in practice. This is a simple one for, or a low grade level for students learning about equations and what it means to have things, adding different quantities together, and they get to play and to try and make this balance. Then this one is the circuit construction kit. This allows students to build pretty much any basically simple circuit they want, and then see what happens when they actually make the proper conditions for electric current to flow. Then they can see how the electrons move, makes light bulbs light up, and change the voltage and see, that makes the electrons move faster and light bulbs brighter, and then they do all sorts of other things. They can add and compare with things in the world around them. So to finish here, I think what we're seeing is now that research is saying that the way we've been doing things for 1,000 years, which was really designed based to transfer information, is not the most effective way to teach when now we're interested in much more important things like complex problem solving and skills. And the new teaching methods that come out of this research are really opportunities for dramatic improvement, and I would say across the education spectrum, but particularly targeting, or we know particularly well how to do it at the post-secondary university level right now, and we know how to do it without it really costing any additional money. It's just teachers changing what they do. So hopefully in the near future, universities will start recognizing that there really is expertise in teaching of their faculty, and start measuring and rewarding and expecting it, and that'll really has the capability of really revolutionizing how our college graduates are capabilities in terms of expert problem solving, and ultimately how the future teachers of the K-12 system also. So, thank you.
感谢 Mr. Carl Wieman 的精彩分享。Thank you, Professor Carl Wieman, for the insightful presentation.